We're going to end chapter 10 here with a topic that's going to feel pretty big and pretty advanced, but the idea is just to give you a little bit of context, kind of everything about phases that we're talking about here. We're talking about spectroscopy. So if you remember from General Chemistry 1, we talked about the idea that energy states in atoms and molecules are quantized. The most common aspect or kind of part of this that you would have learned about is the fact that electrons only exist in particular orbitals around nuclei. So, you have the sort of nucleus that's in the middle of the atom, and then the electrons are moving around out here. That's just a cartoon. This isn't accurate, but they're in these particular orbitals. An electron can move around here, it can move around here, but it can't move around at this distance from the nucleus, right? It has to take these particular states. They are quantized. The states are quantized, means they're countable. So the electron could be in 1, 2, 3, 4, right? You can count what all the states are. So the energy states in atoms are quantized. That has some effects on how we observe and how atoms behave and things like that. And so one of the things that you may have seen is the idea of a flame test, that if you excite electrons, if you put a bunch of energy into an atom, the electrons will go to higher energy states, right? There's those particular quantized states. So they'll go from the low one, say it's, it's calm room temperature, all of a sudden they're going up to higher ones, and then they will fall back down. And so the electrons will relax where they go from the high energy state down to a lower energy state. And so doing that transition from high energy to low energy means energy has to leave somehow, right? Energy has to leave the atom, leave the electron. And it leaves as light, and it leaves as visible light. And so in the case of electrons, it leaves as light that has a energy based on the energy difference between these states, right? That energy difference from 4 to 1, whatever the energy difference was, will determine what wavelength of light, what color of light comes out from the atom. And so each atom has its own unique set of electron states, meaning that each atom has its own unique set of colors that come out. So if you put these metal atoms, so the chloride doesn't do anything in the visible. So the lithium will be red, sodium would be an orangish yellow, potassium is very faint purple, strontium gives you this really, really pretty pink color. There's these sorts of characteristic ideas, and those colors reflect the particular energy differences, the differences in energy between the states that the electrons can be in those particular atoms. This idea of particular wavelengths, particular types of light affecting electrons doesn't just correspond to the light coming out, it also corresponds to light going in. So say you have a molecule, so your electrons are down here in the ground state, in that lowest energy state, and you shine white light. White light means the entire rainbow. So you've got the entire rainbow of light hitting your sample, hitting your system. All of these types of light come in, but only particular wavelengths can excite the electrons, right? Because the white light shines in, but then those wavelengths that corresponded to the gaps in energy are the only ones that will be able to interact with the electrons. If you had a wavelength, we're shining all of the wavelengths, right? If you had a wavelength that went from, say, here to here, that couldn't interact with the electron because it would be putting enough energy into the electron so that it'd be in a place where that state can't exist, right? There are only certain states where the electron can exist, so only certain wavelengths will move the electron, do the excitation from this ground state up into those higher energy states. All the other wavelengths just pass on through. That purple just goes right on through. They transmit through the sample totally unaffected. You did not see them. You won't. They're going to totally pass through. You won't be able to. You'll see them come through the other side. So what this means is we can measure light's interaction with matter in two ways. We can excite atoms and see what comes out. And then we only get those particular wavelengths that can excite where the electrons kind of fall down and emit out. Or we can shine white light, where we shine all of the light, all the different colors of light on our material. And then we can measure which ones don't make it out. And you'll note they're perfect negatives of each other, basically because all the light of this wavelength went into the atoms themselves. All of this light went in, all of this light, all these things went into the atoms themselves. And so you can either you can excite an atom using like fire or something like that and see what comes out, or you can shine light and then see what's missing. But both of these would be characteristic of hydrogen in this case. So these spectra are for hydrogen. One would be the absorption, what light is absorbed by hydrogen, you'll note, and what light is emitted by hydrogen is on the bottom. So both of these are strategies that you could tell to say, hey, this looks like hydrogen. I have some gas, I don't know what it is. You can collect a spectrum, and then you're going to be able to tell it's hydrogen if it matches whichever method you're doing. So that's electrons. All energy descriptions of a molecule are quantized, though, not just the electrons. So quantum mechanics expands to every aspect of molecules. And one of the ones we want to talk about are molecular vibrations. So in a molecular vibration, we can think of the atoms or the bonds acting like springs. So the atoms stay together in a molecule, but they're going to kind of move around relative to each other. Okay? These vibrations, these molecular vibrations, can only happen at certain quantized frequencies. So just like the electrons could only be in certain orbitals, they could only be in certain positions around the nucleus, atoms in a molecule can only vibrate at certain frequencies. Okay? So if you want to cause a molecule to vibrate, you have to put in a very particular amount of energy corresponding to that gap between basically no vibration and the vibrations we got going on here, right? You can go from nothing to starting. There's a particular amount of energy that is required to do that. That energy to cause those vibrations generally corresponds to infrared wavelengths. So with electrons, it was wavelengths of light that were visible light. For vibrations, it's infrared wavelengths. Those are lower energy photons. That's lower energy light. So lower energy photons than visible, because getting molecules to kind of atoms to move is less energy required. So infrared light, when it interacts with molecules, can cause the molecules to start jiggling. And that's actually why you feel infrared light as heat. So we oftentimes think of infrared as like a heat cam, or heat cameras, heat sensors are all measuring infrared light. And that's because it's the light that corresponds to that. It's the light that corresponds to that sort of jiggling. So if you are next to an infrared light source, that infrared light can get into the molecules in your body and make them vibrate, make them jiggle around. They start to move. You feel that as heat. So this is, kind of a practical, you're used, you know this, you have experienced molecular vibrations. So when you have a molecule, so here's the Lewis structure. This is ethanol. Here is the kind of a structure of ethanol that's going to be doing some shaking. So this GIF. So you have all these different bonds in the molecule, and those different bonds are going to have different frequencies that they vibrate at. And so what this is showing is a spectrum, just like we saw with the colors for the visible light. That the idea is basically you shine all of the infrared wavelengths at your molecule, and you see which ones don't make it through. So these wavelengths right here, you can see this would be 100%, if the signal up here, 100% makes it through. So that would mean, those wavelengths, those infrared photons do not interact with the molecule. But these other infrared photons do interact with the molecule. And we can see a lot of them interact with the molecule. And they correspond to either the stretches of the OH or the CH bonds or the CO bonds. And so we can see that there's all of these different atoms in the molecule, and they're all vibrating relative to each other. So again, if you shine the white light, or not white light in this case, but all of the infrared wavelengths on your molecule, and you see which ones get absorbed by the molecule, causing vibrations in the molecule, that gives you the IR spectrum, and that gives you the fingerprint. This idea, spectroscopy, is the most common chemical analysis technique. If you have an unknown substance and you want to figure out what it is, if you take the IR spectrum of it, you can tell, does it match up with what the IR spectrum of ethanol is supposed to be? Because it's always going to look like this. If you get a spectrum that looks like what's popping up in this top, that means it's ethanol, because that is what the spectrum of ethanol looks like. So this is the most common form of, not necessarily IR, you can use other wavelengths as well, but this is the most common form of chemical analysis. So this is the infrared spectrum of water. Water is a pretty small molecule, only 3 atoms, so there's not too many vibrations going on just because they can't really move around. There are 3 types of vibrations that can have, there's 3 vibrations, there's 2 types of them. There are the stretching vibrations. They can either stretch asymmetrically or symmetrically. This is just, you can see it's OH bond length changes. These GIFs are potentially over-exaggerated. Then there's also the bend or scissor mode, where the bond length isn't changing, so the bond length is not changing there. Instead, the angle is all that's changing. And so if you had a sample of water and you took its infrared spectrum, you would see this is the overall kind of spectrum that you get. And in this range of wavelengths, we can see for a wide range of IR wavelengths and infrared energies, it gets absorbed, right? Implying that there's a lot of types of states there. This is a very sharp peak. And if you remember when we were looking at the hydrogen absorption, that visible light stuff, it was really sharp lines because there is one particular energy gap between those electron states. But we're seeing a really wide gap here. This is a really huge range of energies, which means there's a lot of molecules that have these sorts of, this vibrational gap, this vibrational energy has a lot of kind of variability to it. There's a lot of different kind of flavors and a lot of different different situations where these water molecules are in, that they can absorb different energies of infrared light. And so this idea, if we focus in on this part of the infrared spectrum of water, we can see that the OH stretch frequencies strongly depend on the state of the water molecule. So this is all still the OH stretches. So I only have one of them here, the asymmetric one. But we're looking at OH stretches, basically those bonds getting longer or shorter. I do want to note this has swapped. This is an inverted axis. So it's the same idea, but we were previously looking at things going down for signal. Now we're looking at things going up. But someone just inverted it. People have different preferences. But you can see these are all water, with the difference being it's a vapor, which is in red, a liquid, which is in green, and solid ice, which is in blue. And so all of these are shown all on the same graph. And we can see we're getting different appearances, right? This fingerprint is changing, right? This is supposed to be characteristic of water. So what's going on? Well, if we think about it, in gas, we're seeing these really sharp peaks, right? There's not really blobby, right? There's very particular energies that we're seeing these transitions happen at. Some of the kind of roughness of it, the variability, there's some kind of fancier physics going on. But in this case, there really is just, the water molecules are all in very particular situations, right? There is a lot of very few possible frequencies of the vibration, which means a lot of the molecules are really looking the same, right? There's not that many different varieties of molecules, and it's because they're not interacting with other molecules. It's a gas phase, so they're all by themselves. In the liquid, we have this really big rounded peak. That big rounded peak, there's a huge range of frequencies of the vibrations, right? If you remember this idea of the energy of the infrared wavelength is going to correspond to the frequency of the vibration that it's causing. And so there's a bunch of different frequencies of vibrations of OH bonds because there's a lot of intermolecular environments that those molecules are in, right? They're jammed up with a bunch of other molecules. They're forming hydrogen bonds with other molecules. There's a bunch of different types of hydrogen bonds, a bunch of different types of interactions. They're all just kind of jammed together in there. And similarly, ice has a big, large peak. It's not sharp like the gas phase was, but it's much more defined than the liquid. So there's, some variability because the water molecules are interacting with other water molecules. There is, intermolecular interactions. There are hydrogen bonds, but it's a smaller range. It's a much more narrow peak up here. And there's kind of some structure. You can kind of see there's like this kind of water molecule, and then there's this kind of water molecule. And there's a range, there's kind of two kind of hills that are overlapping together. And so this really is reflecting what we've talked about for this molecular description of our phases. In liquids, these molecules move around and they interact with other molecules. Forming hydrogen bonds is going to affect the frequency of that vibration, right? If the OH bond is stretching, you know, what is it stretching into? What is that hydrogen interacting with? Is it forming an interaction with another molecule? Is it forming what's that there? Does that make the OH bond harder to vibrate or easier to vibrate? Does it make it vibrate with a higher frequency or a lower frequency, right? The idea is that intermolecular environment affects what's going on. And so in this GIF over here, it's just a model of freezing liquid water. And so you can see initially the water molecules are just impossible to follow, right? They're just moving around randomly. That fact that your eye cannot follow individual water molecules is showing you that there's a lot of different environments, right? There's a lot of randomness. And that's why you get that big blob in the IR spectrum. When it starts to form a solid, you get those hexagonal shapes. Yes, they're forming hydrogen bonds, and they're all still moving around. This is anything from rigid, right? They are moving around plenty, but they're much more rigid than the liquid. It's much more consistent, right? Each water has a consistent kind of bonding partners or hydrogen bonding partners that it's kind of lined up with. And so it's always forming certain types of bonds, but it's not, or forming certain interactions, but it's not really moving around willy-nilly. It's not total randomness. You can also see that this is not accidental. They are forming little hexagons in here. But there's little hexagons forming in the ice. That's why snowflakes have six-fold symmetry, right? Because they're made of ice. Ice at its atomic level has six-sided symmetry. It's going to have six-sided symmetry at a macroscopic level as well. So one of the other reasons why I want to talk about this is we've talked a lot about this kind of molecular description. I've put up a lot of images of molecules in solids, liquids, and gases. It's important to note that that comes from experimental ideas. We cannot take photos of molecules. We can collect spectrum. We can collect really high resolution spectrum. We can do really good experiments. And those experimental results are what tell us that, hey, there's something going on between these phases. So we collect these experiments. This is reality. These graphs are boring. They're not very necessarily insightful, and they need to be interpreted, but this is reality. This is what these molecules are doing. This is just a mathematical model that is approximating reality. That's picking out a part of reality that I want to show you, and that's what this model is giving us. But this is still purely a mathematical model, and that's all it is going to still be at the end of the day. And the most important thing is that that model helps us understand and explain reality. But it's not just, it doesn't exist on its own. It's not something we just made up or thought up. It's something that is used to support and explain reality. But importantly, everything's still based in these real experimental measurements. Congrats! Made it to the end of chapter 10. The final slide in each video will be this kind of recap slide, which features kind of the skills or kind of goals of what you're supposed to take away from each of the chapters. These are also given on the week pages for Blackboard, so you'll note like this is all of chapter 10, but the stuff like liquids, which was like right here was the dividing line, this was in the week 1 content, this is in the week 2 content down here. So the idea is just kind of a guideline of, you know, kind of you can prep before you watch the videos, like what the most important things are when you're watching videos. And then also if you're like going back and studying for the tests or whatever, the things that are the most important thing for each week are also like the most likely things to show up on the tests kind of stuff. So can you do all of these things? Can you perform all of these actions? That would mean you like know everything that's important out of chapter 10. There you go. That is it. 3 questions on participation 9-1. You want to find all 3 of those questions, get them answered, and get those answers submitted by Tuesday night. Then Wednesday, midweek homework is due covering this set of videos. this last part of chapter 10. And then we'll do evaporation and intermolecular forces on Wednesday. Because it's a full kind of standard week, the notebook needs to be set up before lab starts on Wednesday. So whoever's the leader and the technician for this week need to get their part set up. And then the pre-lab and the pre-lab questions and the technique comprehension are individual assignments. It's questions on Blackboard where you will either answer questions about the lab handout or questions about a video about how to do a technique associated with the lab. If you have any questions about how to do anything or how any of the assignments work, please don't hesitate to reach out. Otherwise, there will be the answers to the Tuesday participation that go live on Tuesday night. Otherwise, that is it for me. Enjoy the rest of your day. I'll see you later this week. Bye-bye.